Okay, so in this video we are going to look at some remarkable properties of the Bell state. So the property that we'll be interested in is what's called the rotational invariance of the Bell state. So remember what the Bell state is. It's a state of two qubits where they are in a equal superposition of being in the state 0, 0 or 1, 1. So now you remember that if we measure the first qubit, if we see a 0, then if we measure the second qubit, it's also going to be, we are going to see it in the state 0 with probability 1. Now, what the rotational invariance of the Bell state says is the following very remarkable property. What it says is, suppose that we were to measure this Bell state so that's our basis 0, 1. Instead of measuring it in this 0, 1 basis, let's measure it in some basis u perp, where u and u perp are just arbitrary rotations. This is just some arbitrary angle here with the 0 state in the real plane. And we do the same thing for the other Bell state. We measure this one, the other qubit in the Bell state. We measure it also in u perp. Okay? The remarkable fact is that if we are to carry out this measurement, well, first of all, we'll see u or u perp with equal probability, with 50-50 probability. Okay, so the probability that the outcome is u is 1/2. Probability is u perp, it's also 1/2. But if the probability we see the first outcome is u, if that's what happens, then when we make a measurement on the second qubit, we'll also see u with probability 1. So in other words, we'll always see matching outcomes in the two cases, even though if we look at any one case, it's 50-50 whether we get u or u perp. So this is exactly the same situation we had when we measured in the 0, 1 basis, except it holds no matter what the basis is. Okay? This remarkable property is called the rotational invariance of the Bell state. So now, let's try to understand this a little more. Let's see how well we understand this. So let's say that we make a measurement on this first qubit in some arbitrary basis u perp. And now we pick a different basis. So we pick some different basis v perp for the second qubit, and we measure it in this basis. Okay, so let's say this was u and this angle is theta. So what we want to know is, suppose we do these measurements. We measure the first qubit of the Bell state in this u perp basis. We measure the second qubit in the v perp basis, where these two bases make an angle of theta with each other. Now what we want to know is, what is the probability of matching outcomes? Where we say that the outcomes are matching if we get this outcome on the first qubit and that outcome on the second qubit, or if we get this outcome on the first qubit and that one on the second qubit. Right? So we'll say this matches with that and u perp matches with v perp. So what's the chance that we'll get matching outcomes? Well, I claim that we already, from what we saw in the last slide, we already know how to answer this question. Why? Because when we measure the first qubit, we either get the outcome U or U perp with 50-50 probability. So it doesn't matter which one we get. Let's say we got the outcome U. Now what's the state of the second qubit? Well, I claim the second qubit is in the state U. Right? That's what we saw in the previous slide. But now this is the state of the second qubit, and we are measuring it in the VPerp, VVPerp basis. What's the chance we get outcome V? Well, the answer is exactly cosine squared theta. Okay, so the same thing, the same reasoning holds if we happen to get U perp in the first, as the outcome of our first measurement. Well, then the state of the second qubit must be U perp as well, because they completely match. But now if we measure the second qubit in the VV perp basis, what's the chance we get output V perp? Well, it's still cosine squared theta. So the answer is, if we measure the two qubits in bases which make an angle of theta with each other, the chance that we get matching outcomes is exactly cosine squared theta. Okay, so how do we prove this? Well, the way you prove this is by saying that if you were to write your state psi, it's an equal superposition of 0, 0 plus 1, 1. In the last lecture, we saw that we could also write it as an equal superposition of plus, plus, and minus, minus. What we are claiming is, in fact, if you have an arbitrary U perp, then you can write 0, 0 plus 1, 1 as U perp plus VV perp. Okay, so just think of U as being some arbitrary vector A0 plus B1, where A and B are real numbers. And then U perp you can write as B times 0 minus A times 1. Actually, the way I have drawn it here, it's minus B times 0 plus A times 1. And now what you would do is you would substitute this into this formula, and you'd say, well, what's 1 over square root 2 times U perp? It's just A0 plus B1 times A0 plus B1 plus 1 over square root 2 times U perp, which is minus B0 plus A1 times minus B0 plus A1. And if you expand this out and you simplify, you'll get 1 over square root 2 times 0, 0 plus 1 over square root 2 times 1, 1. Let's see, should I leave this as an exercise? Well, here's the other condition we have. Of course, U and U perp are unit vectors. They have a normalization condition, which is A squared plus B squared equal to 1. Okay, so let's just eyeball it, and let's see, what's the amplitude of 0, 0? Well, there are two ways of achieving 0, 0. The amplitude here is A squared. The amplitude from here is B squared times 1 over square root 2. So it's 1 over square root 2 times A squared plus B squared. But A squared plus B squared is 1, so you get total amplitude is 1 over square root 2. The same thing holds for the amplitude of 1, 1. It's A squared plus B squared, and so that's times 1 over square root 2. What about the amplitude of 0, 1? Well, you achieve 0, 1 from here with amplitude AB times 1 over square root 2, and from here with amplitude minus BA. So these cancel, and so you get amplitude 0. Okay, the same is true for 1, 0, and so you get that the Bell state can be written in any basis as U perp, UU plus U perp, U perp. Now, there's one other thing that I should say, that here I use a restriction that this U perp basis has to be a real valued basis. Okay, so the A and B, the coefficients here are not allowed to be complex valued. If you do want to use complex coefficients, then you can use a different kind of Bell state. This Bell state is called psi minus, and it's of the form 1 over square root 2, 0, 1 minus 1 over square root 2, 1, 0. And this Bell state is actually invariant under any change of basis. If you measure it in u perp, where u is now of the form alpha 0 plus beta 1, where alpha and beta are complex numbers, and u perp is minus beta star 0 plus alpha star 1. These are complex conjugates. Of course, they satisfy this condition, alpha squared plus beta squared equal to 1. And now you can actually verify, if you like, that the same sort of rotational invariance holds, except now it's not just real rotations but also complex rotations in the complex plane. But this is not, if you don't follow this, it's okay, because we are not going to be dealing with this. For the purposes of this lecture, we are only going to be dealing with real rotations, and what I said so far is all that you need to know.